All right, welcome to another great episode from Schmidt Kim. Here we're looking at AP topic 5.1 and 5.5. We've already talked about in the previous video the relationship between the rate of a chemical reaction and experimental parameters. And we looked at 5.1.8.1, looking at defining the kinetics of a chemical reaction as being the rate at which the amount of reactants, and we said the amount of reactants is going to be measured in concentration and how concentration changes per unit of time. And then we looked at 5.1.8.2, looking at the rates of change of reactant and product concentrations are determined by the stoichiometry in the balanced chemical equation, and we wrote rate expressions. Here we're going to look at 5.1.83, and we're going to look at the rate of a reaction and how that is influenced by reactant concentrations, temperature, surface area, catalysts, and other environmental factors. But in doing that, we're going to also look at topic 5.5, the collision model, because we really can't separate this idea from the collision model. Because as we look at concentrations, temperature, surface area, and catalysts, we have to explain those in terms of collisions. In particular, we're gonna explain those how these collisions affect rate, and then and how those collisions, how the frequency of those collisions, the energy and orientation of those collisions affect the outcome of a reactants reacting. Will the reactants be effective or not? And so we're going to take a look at those things. And so here we're looking at 5.5.A.1. We're looking at the elementary reaction to successfully produce products. Reactants must successfully collide to initiate bond breaking and bond making events. And then most reactions, the collisions, only a small fraction of those collisions lead to a reaction. And so successful collisions, or what we say effective collisions, must have the sufficient amount of energy to overcome the activation energy requirements, and they must have the correct orientation. And then we can use our good old-fashioned Maxwell-Boltzmann distribution to kind of explain these things. All right, so let's go ahead and get started. And so let's look at this part right here. We're looking at 5.1.8.3. And again, this is going to go into 5.5 just naturally, looking at the collisions. But we can look at several experimental parameters that have a direct measurable effect on how fast a reaction proceeds, and they are governed by the collision theory. This is why we're talking about 5.5, because we cannot talk about how these things affect the rate of the reaction without using the collision theory. And the collision theory states that when that reactions occur when reactant particles collide. So in order for a reaction to occur, reactant particles must collide. But that's only part of the story, because when they collide, they have to also collide with a sufficient amount of energy and the correct orientation in order for those collisions to be effective, meaning that they're going to then produce a product. And so most of the collisions that we see, or most of the collisions that occur, do not meet this criteria. And so we're going to take a look at that as we're there. But obviously, we see chemical reactions take place. So there are particles that do collide with sufficient energy and the correct orientation. Otherwise, we wouldn't see reactions take place. Now, things to just kind of look at on this, I put this graphic here. The two things that we're looking for are going to be sufficient energy and then correct orientation. So here we have a collision, and again, that's one of our major things, is that a collision has to take place. So here's our reactants. They're going to collide, and they're going to collide in the correct orientation. All right. If we look at the one where there's a reaction produced, we see that this was the orientation that they collide. So they're colliding with the correct orientation. However, they don't have enough energy for that collision to be effective. And so what we end up with is no reaction. And then over here, we see that these are going to collide maybe with sufficient energy, but it's not going to be in the correct orientation. and because the orientation of the molecules when they do collide will not produce a product, and so we would say also no reaction. So both have to be true. The particles have to collide with sufficient energy. So here these are saying this is going to collide with sufficient energy. They're in the correct orientation. And now we get something different in the as the products. We have a reaction. And so we have a new molecule formed and another atom formed. And so we see that both criteria have to be met, and that they have to have sufficient energy with collision, and then the molecules have to be oriented so that when the collision takes place, that there is going to be a reaction. So those two things have to happen, and that is the collision theory, uh, um, kind of summed up real quick. All right, so let's take a look at how concentrations affect the rate of a reaction, and we'll also take a look at that in light of the collision theory. So in general, the concentration of reactants increases the frequency of effective collisions. When we say effective collisions, that means the collisions have sufficient energy and the correct orientation. So when we increase the frequency of collision, so here we have a we have two vessels, one with fewer particles in it and one with more particles. One that is, we would say, has a low concentration, whereas one has a higher concentration. So in the lower concentration vessel, uh, because there's so few particles in there, the frequency at which the particles are going to collide with one another is going to be very, very low. And if the collisions at which they collide is very low, well, then the chances of having an effective collision, meaning a collision that has sufficient energy and the correct orientation, is going to be even lower. And so, if we just look at that particles will collide more frequently, well, then we can make the case that then they will have more effective collisions because there's more collisions that take place. But when they don't collide, because the concentration is low, there's no chance at an effective collision when collisions don't take place. And so this has fewer collisions that take place, and so that's going to have even fewer effective collisions. And so a reactant concentration is low, it decreases the opportunities for effective collisions because collisions aren't taking place. All right. So it decreases opportunities for effective collisions to take place in a given period of time due to particle collisions. So reactants with the correct orientation and sufficient energy to react will collide less frequently. And if they collide less frequently, well, then it's going to take a longer period of time for all of the reactants to react to produce products. And so we would say lower concentration means that this is a lower rate. And on the other side of things, when we have more particles, then we're going to see that the particles will collide more frequently. Does that mean that all of those collisions are going to be effective? No, but just by virtue that they're colliding, we're going to see that we're going to have an increase of effective collisions versus when we had low concentration. And so that means when we have a high concentration, the opportunities for effective collisions to take place in a given period of time due to particle collisions will increase. And so reactants with the correct orientation and sufficient energy to react will collide more frequently. And so we can see that in low concentration, particle collisions are less frequent, whereas in high concentration, particle collisions are more frequent. So less frequent and more frequent. And so the more frequently that the particles collide, the better opportunity for effective collisions to take place. This means that it will take less time for the reaction to go to completion, and so a higher concentration will lead to a faster rate. And so that's what we need to know as far as concentration goes on this essential knowledge here. The next one that we're going to look at is temperature. So if we look at temperature, temperature we say increasing the temperature dramatically increases the reaction rate. So higher temperatures increase the kinetic energy of particles, and we could say increase the average kinetic energy of particles, leading to more frequent collisions. Again, we talk about the frequency of collisions. If they collide more frequently, well, then we are going to say that there's going to be a larger opportunity for effective collisions to take place. Okay, so we see that they collide more frequent at higher temperatures, and then a larger fraction of molecules possessing the necessary activation energy to react. This activation energy is the amount of energy needed for those reactions to react. We said over here before, we said sufficient energy. When we say it's sufficient energy, we're referring to the activation energy. So do they have to have the correct orientation, but the particles also have, the reactant particles also have to have sufficient energy. And that energy, if we give it a name, is called the activation energy. And so we go back to our Maxwell-Boltzmann distribution. What we notice is at temperature 1, the average kinetic energy is lower. And so we could see than what we see in T2. If we look at T2, go to the top of the curve, we see the average kinetic energy is higher. Now, how does that affect the reaction rate? Well, if we look at it in terms of the energy of activation, and we drew this line saying this is the amount of energy needed for a successful collision to take place, we can see everything under the green line, all particles under the green line, including the blue, will have enough energy to make a successful or effective collision. However, at the lower temperature or the lower average kinetic energy, only the particles under the blue will have enough energy to react. So we can see that a larger fraction of particles at higher temperatures have sufficient amount of energy for that reaction to be effective. But sufficient amount of energy is only one criteria. But we can say that if more particles or a larger fraction have enough energy, well, then it's more likely that they're going to also collide in the correct orientation. And so we would see the reaction rate increase with higher temperatures. So that is one way of looking at that in terms of a Maxwell-Boltzmann distribution. We look at it through an energy diagram. We see that here's the energy of our reactants, and then we notice here the difference between the start potential energy at the start, and then here's the activation energy. And so we see that in order for this reaction to take place, yes, they have to have the correct orientation, and we can kind of see that these are kind of going to align that way. We have a carbon going to maybe collide with that oxygen, and we could see that that could produce some of our products, the carbon dioxide. However, if that carbon were going to collide with the nitrogen of that same molecule, well, then we would say the orientation is not correct. And so even if it had enough energy, it wouldn't be a successful collision. But we're not talking about orientation here as much as we are talking about energy of activation. So we see the energy of activation is this value right here from the beginning to this transition state. Once particles have this much energy here, we say they have enough energy for the energy, or they have the activation energy. And so the reaction can be effective with regard to the amount of energy that the particles are colliding with. And so that's what that is. And so we determine this energy of activation, and we'll be going over that again in Unit 6 and how we determine some of these things, whether the reaction is endothermic or exothermic. And we're going to spend a little more time on this diagram even here in Unit 5. But what we notice then is here's activation energy on a Maxwell-Boltzmann, and then here's the activation energy on an energy diagram. They are relating to the same thing. This one is just simply informing us of the amount of energy, but the Maxwell-Boltzmann distribution is a little bit better for our explanation, especially with regard to the AP curriculum, because it says that we need to understand that a larger fraction of particles will have a sufficient amount of energy to go ahead and react. And so this Maxwell-Boltzmann distribution can show the number of particles increases with an increase in the temperature. Again, there's another little graphic here. There's some problems with this graphic. One is that in a sample, we just looked at a Maxwell-Boltzmann distribution, that not all particles have the same amount of energy or have the same velocity. And so these arrows are all drawn in this sample with the same length, and the same thing here. But I think what we're trying to just say is the average is a lower temperature, the average is a higher temperature, but this particular diagrams are not to code, if you will. But the rest of it looks pretty good. Particles have less kinetic energy, making collisions on average lower in energy. And if they're lower in energy, then there's going to be fewer particles with the amount of energy needed for a successful collision, ergo a slower rate of reaction. However, if the temperatures are higher, particles on average have higher energy, and so there's going to be a larger fraction of particles that have sufficient amount of energy, meet the activation energy, and go ahead and react, and that will allow the reaction rate to be faster. And so that's the idea of looking at 5.1 and understanding, number one, we looked at concentration. Now, number two, we look at temperature, and how, and in both cases, we've looked at collisions and how those collisions affect the rate of reaction. And so when we have higher concentrations, we see higher opportunity for collisions to take place. And so we're going to see that the reaction rate increases. When we see higher temperature, again, particles are not only moving faster, but they are going to have enough energy when they do collide, or a larger fraction of particles will have enough energy when they do collide to go ahead and react. Well, one thing I did not mention that is directly stated in the standard is that in this case, especially looking at this, that actually most of the particles in the sample do not have enough energy to react. So it's just a small fraction that do. If we move the average over to where the activation energy was, well, then we see a larger sample. So it really is temperature dependent. All right, and then let's go back just a quick bit. The next thing that we're going to look at, so we've looked at concentration, temperature. The next thing we're going to look at is surface area. And surface area, let's see here, surface area, we're going to look at, for surface area, for reactions involving a solid reactant, increasing the surface area exposed to other reactants, such as crushing a solid into a powder, increases the reaction rate. This allows for more contact points where collisions and reactions can occur. So if we have these three samples here, see this large chunk. Well, this large chunk actually has what we say a low surface area. So there's very little surface exposed that can react. As a matter of fact, there's a lot of reactant inside the cube that does not have exposure to the other reactant, and therefore it can't cause a reaction because it's not exposed. And so we say it has low surface area. Whereas if we have a powder, we're going to see that all surface areas of these tiny little dots, these powder, they're all available to react. And so we say the surface area is high. And so if these particles all have more surface area, then there's more contact points, more areas for to react. We're going to have a faster rate of reaction versus where we have fewer contact points and the reactant doesn't have the ability to react. A better picture of that may be here. Here, this is low surface area, and we can see that only this area right here can react. Everything in the center can't. But over here, if we were to measure the circumference of all of these, we would then see, wow, that is a much larger area than what we see on just this one. And it's and this is just 4 pieces of the same pie. So what we're going to then see is that this has more contact points, more areas where reactant particles can collide, And so then we're going to see a faster rate. And so that's how surface area affects the rate of the reaction, because there's going to be more areas for collisions to take place. And if there's more collisions, then there's more effective collisions. All right. And so a higher surface area will lead to a faster rate. We just need to make sure we understand the concept of surface area. And then the last thing that we have to go over is going to be catalysts. In catalysts, we're going to bring this up again within this unit, but we want to understand how they affect the rate of a reaction. A catalyst is a substance that increases the reaction rate without being consumed in the overall reaction. It works by providing an alternative reaction pathway with a lower activation energy, thereby increasing the fraction of effective collisions. Okay, so very important. The statement right here uses language that you will find on your test. Catalysts, they increase the reaction rate without being consumed. They are not a reactant. Catalysts are not reactants. They are there to help provide an alternative reaction pathway. And what they actually do in increasing the rate of the reaction is they lower the activation energy of that reaction. And so if we go back to our Maxwell-Boltzmann distribution, here is a reaction, and we're not going to change the number of collisions. We're not going to change the concentration. We're not going to change the average kinetic energy. We're not going to change the surface area. The only thing we're going to do to this reaction is add a catalyst. And so we can see the temperature remains constant, but now we have, instead of having an activation energy way over here at high energy, now we have an activation energy that is lower. And so when we have an activation energy that is lower, the reaction can take place here. Why? Because of the presence of a catalyst, it lowers the energy of activation. And so we can see that everything in the green and blue will have sufficient energy to react. Why? Because the catalyst lowers the energy of activation. All right. Whereas before the catalyst was introduced, only the particles in blue could react. They had sufficient energy to react. This does not speak to the orientation of the molecules, but only the amount of energy needed for the reaction to take place. And sometimes catalysts they can also help with orientation, which then helps with lowering the activation energy. Not a major point that I'm going to bring up here. But if we look at the same Maxwell-Boltzmann distribution, and again, I told you we can look at this in two ways. We can look at this in an energy diagram as well. And this is a more common look. But what we see is the energy of activation of the uncatalyzed reaction is very high. And so in order for this reaction to take place, this much energy would need to be, the reactants would need this much energy. And so in the presence of a catalyst, they only need this much energy. So the amount of energy needed for a successful collision is lower in the presence of a catalyst. And what is the impact on that? The impact is when the energy of activation is lower, a larger fraction of particles then have enough energy for a successful collision. And so what we're looking at, again, the average kinetic energy is the same in a catalyzed and uncatalyzed reaction. The total number of collisions remains constant in both of those. But we see the fraction of effective collisions between reactants increases in the catalyzed reaction because not as much energy is required for a successful collision to occur. It creates an alternative, this is a great one, an alternative reaction pathway that lowers the energy of activation. All right, and then the rate of the catalyzed reaction is greater because it has a lower activation energy. And so that brings us to the end of Unit 5.1 and all of Unit 5.5. I thank you for watching another great Schmidt Chem episode. Thank you for watching, and please like and subscribe.